All right, guys, Mr. Antonucci here, and in this video, we're going to talk about rates of change in the derivative, and in particular, we're going to start off by talking about equations for the tangent line and normal line to the graph of a function. So previously, back in chapter 1, we talked about this tangent line problem. This is where you're given a function f and a point on its graph, and you want to know what is the slope of the line tangent to the graph at that point. Well, how we begin this process is we pick another point, call it Q, to the right of the point P on the graph, and we calculate the slope of that line going through those 2 points. Now, that's going to be the secant line here. And in function notation, it's just f of x minus f of c over x minus c. And again, this is just the formula for slope in function notation. Remember y2 minus y1 over x2 minus x1. So here we have the graph in black of f of x equals 0.1 times x squared. The point P that we want to try to find the equation of the tangent line at is when the x value is 1. The tangent line here is in green, and the secant line, which goes through another point, is in orange. If we start at the point when x is 6, the slope of this tangent line is just y2 minus y1 over x2 minus x, or f of a minus f of 1 over a minus 1. And in this case, a is 6. Now, as I let this second point get closer and closer to the first one, notice how the secant line, the slope starts to line up the slope of the tangent line in 2 ways. Geometrically, you could see that this orange line is getting closer to the green line, and also this slope formula here, which is at 0.33 right now, is getting closer and closer to the slope of this tangent line. As I take A and let it approach 1, you could see that the slope of the secant and tangent lines are getting closer and closer and closer. Now I can only get so close, or they'll be right on top of each other, and it would be undefined because you need 2 points to get slope. As I let A get closer and closer to 1, the slope of the secant line is going to get closer and closer to the slope of the tangent line. So it looks like as A approaches 1 here, if we watch the slope number looks like it's getting closer and closer to 0.2. So my guess would be that the slope of the tangent line is 0.2. So if you think about it, what we really did was took the limit as that second x value approached the a value, or the c value in this case. And this is how we define the tangent line. The tangent line to the graph of f at the point P is the line containing the point P, which is c comma f of c, having the slope right here. Notice this is the limit as x approaches c of the slope formula for the secant line, provided that limit exists. Now, this limit that defines the slope of the tangent line is extremely important. In fact, it has its own special notation called prime notation. So we read this as f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. Now, to actually find the equation of the tangent line, it's just the equation of a line. So if that limit exists, the slope of the tangent line, or f prime of c, then an equation of the tangent line to the graph at that point is given by this formula here. Another way that this is sometimes written is y equals f of c. They just solve it for y. So they add this f of c to the other side, plus f prime of c times x minus c. Now, this is really just point slope form of the equation of a line in function notation. So in point slope form, this would be y equals y1 plus m times x minus x1. So the c comma f of c is really just your x1, y1, and the f prime of c is the slope m of the tangent line. In some application, the line that's perpendicular to the tangent line is what's needed, and this is called the normal line to the graph of f. You're familiar with getting equations of the normal line. You don't have to have another equation to memorize. The normal line is just perpendicular, and so the Slope of a line perpendicular to another line is just the opposite reciprocal. So in particular, if we look at this -1 over f prime of c, remember the slope of the tangent line was f prime of c, so the slope of the normal line is just the opposite and the reciprocal. Also, another way to think about it is when you take the product of slopes of lines that are perpendicular, you get -1. So in other words, the slope of the tangent line times the slope of the normal line would equal -1. This is just point slope form with function notation. Now let's actually go through an example here where we have to find equations of tangent and normal lines. So first thing we want to do is find the slope of the line tangent to the graph of f of x equals x squared at the point -2, 4. So for part A, we are asked for basically f prime of -2. This is going to be equal to the limit as x approaches -2 of f of x minus f of c, so f of -2, over x minus c, so x minus -2, which is x plus 2. Now, if we plug the values in that we have, we would have limit as x approaches -2. The denominator is just going to be x plus 2, x squared minus f of -2, that's going to be 4. And if you notice, the numerator here is a difference of squares. If we tried to take the limit as x approaches -2, you'd have 0 over 0. So we could factor the numerator and have x plus 2 times x minus 2 all over x plus 2. The x plus 2's cancel, and so we have the limit as x approaches -2 of x minus 2, which is -4. So that is the slope of the tangent line. Now for part B, we want to use the result from A to find the equation of the tangent line at the point -2, 4. So this is going to be y equals y1, which is the y value 4, plus f prime of -2, which is -4, times x minus -2, so x plus 2. If we solve this for y, you would have y equals -4x minus 4. Part C, we want to find the equation of the normal line. So we could just take our tangent line, and all we need to do, because it's the same point, is take the opposite reciprocal of the slope. So that's going to be positive 1/4 times x plus 2. And if we solve that for y, you would have y equals 1/4 x plus 9/2. So there we go. And then the last thing we want to do is just kind of verify graphically by graphing everything in Desmos. So here I have the graph of x squared in the point -2, 4. One thing you can note is that at this point, the graph is decreasing, so its slope should be negative, and that makes sense with what we determined from finding the slope of the tangent line to be -4. So if we graph that, we would have y equals -4x minus 4, and there we go. And then the normal line is going to be y equals 1/4 x plus 9/2. We want to talk about finding the rate of change of a function. Now, before we talked about the average rate of change of a function, which is just f of x minus f of c over x minus c. Now, this might look very familiar to what we just talked about, which is the slope of the secant line. This is just function notation for the slope between 2 points. You can think of this as y2 minus y1 over x2 minus x1. Now, the average rate of change describes how a function changes over an interval. However, we often want to understand the behavior of a function at a specific number or a specific moment in time. For this, we're going to use what's called the instantaneous rate of change. If we look at the definition here, the instantaneous rate of change of f at c is the same exact definition as the slope of the tangent line. Let's go ahead and do an example. We want to find the rate of change of the function x squared minus 5x at c equals 2, and then at any real number c. Part A, c equals 2, the function f of x is x squared minus 5x. F of 2 is going to be 2 squared minus 5 times 2, which is -6. So f prime of 2 is the limit as x approaches 2 of f of x, which is x squared minus 5x, minus f of c, which is negative 6, all over x minus c, so x minus 2. Simplify this a little bit. You have the limit. The numerator would simplify to x squared minus 5x plus 6 over x minus 2. Again, using direct substitution, this limit would give you an indeterminate form. Since we have a rational function, we can try to factor. The numerator is going to factor into x minus 2, x minus 3. We need factors of 6 that add to negative 5, so they both have to be negative. Over x minus 2, and we can see that the factor of x minus 2 cancels. Then we have the limit as x approaches 2 of x minus 3. We can evaluate that and get negative 1. So we would say that the rate of change of f at c equals 2 is negative 1. For part B, if we say c is any real number, we don't plug an actual numerical value in. We just use c in place of x. F prime of c is going to be the limit as x approaches c of f of x, which is x squared minus 5x, minus f of c, which is just going to be c squared minus 5c, over x minus c. If you let x approach c and use direct substitution, the numerator and denominator would both approach 0. Again, since we have rational functions, we should think to factor this. We know the denominator is going to be x minus c. If we rearrange some of the terms in the numerator, we can have x squared minus c squared minus, if we group the 5x and the 5c and factor out the negative 5, you'd have negative 5 times x minus c. This is going to be the limit as x approaches c, x minus c. This x squared minus c squared is a difference of squares, so that's x minus c times x plus c minus 5 times x minus c. And this is the limit as x approaches c, x minus c in the denominator. Notice that you have a factor of x minus c here and a factor of x minus c here. So if we factor out the x minus c, you would have x plus c minus 5 left over. Now you can see that the x minus c's cancel, and our limit is x approaches c of x plus c minus 5. And if we take the limit as x approaches c, you would have c plus c minus 5, which is 2c minus 5. So this would represent the rate of change of f of x at c for any number. And in fact, we could just plug in any number we want for c, and that would give us the rate of change at that particular c value. Let's look at an example where there is an actual context. So in a metabolic experiment, the mass m of glucose decreases according to the function m of t, where m is measured in grams and t is the time in hours. First, we want to find the reaction rate m prime at t equals 1 hour, and then interpret that value in context. For part A, m prime of 1 is going to be the limit as t approaches 1 of m of t minus m of 1 over t minus 1. M of t is 4.5 minus 0.03 t squared. And then if I plug 1 in, I would have 4.5 minus 0.03. Combining like terms, negative 0.03 t squared minus 0.03 over t minus 1. If factor a 0.03 and a negative out of the numerator, then that t squared minus 1, we could factor that as t minus 1 times t plus 1, because it's a difference of squares, and then the t minus 1s are going to cancel, and this simplifies of negative 0.03 times t plus 1, and as t approaches 1, t plus 1 is going to approach 2, that multiplies the negative 0.03, and you get negative 0.06. Now, because this problem is in context, the negative 0.6 would have units. And think about how we developed this. We did the change in mass divided by the change in time. So the units are going to be grams per hour. That is our answer to part A. Part B asks us to interpret this value in context. So what this means is that the mass m of glucose at t equals 1 hour is changing at a rate of negative 0.6 grams per hour. Or we could say it's decreasing at the rate of 0.6 grams per hour. When you interpret it, make sure you interpret it in context in terms of the values used and the units on your final answer. All right, guys, that's it for this one. Hope that was helpful.